Good morning. So we will discuss about the Module A, acid, bases, and solubility equilibria. Concept of acids and bases. Aqueous acids are compounds containing hydrogen and when dissolved in water, releasing this hydrogen ion, H positive, in an aqueous solution. Areous bases are compounds that releases hydrogen ions, OH negative, when dissolved in water. Hydrochloric acid and sodium hydroxides are example of acid and a base. Svante Arrhenius, a Swedish scientist, proposed that compounds separate into their individual ions as they dissolve in water. He also suggested that compounds containing hydrogen would release the ion when dissolved in water. When an Arrhenius acid reacts with an Arrhenius base, it will yield water and salt, commonly referred to as the neutralization reaction. The Bronsted-Lowry concept offers a more general definition of acids and bases. A Bronsted-Lowry acid is a substance capable of donating a proton H positive, while Bronsted-Lowry base is a substance capable of accepting a proton. Consider the dissolution of gaseous hydrochloric acid and water. So this one is the hydrogen and the chloride, now it's hydrogen and oxygen. So this is the how it goes. So notice that the reaction yields a chloride ion and a water molecule with an additional hydrogen molecule. This positively charged ion is called the hydronium ion, so H3O flat positive. Based on the Bronsted-Lowry concept, HCl is the acid proton donor and H2O is the base. Conjugated acid can be defined as the substance formed when the base accepted the proton. A conjugate base is the substance formed after the acid loses its proton. Consider the complete dissociation of hydrochloric acid in water. The conjugate base is the chloride ion and the conjugate acid is the protonated water. The identification of conjugates is simply by definition. Now let's consider the dissociation of ammonia in water. Notice that this reaction is reversible. This means that the reaction can proceed from left to the right of the reaction or vice versa. This is the depending on the condition on the reactions. This also means that we have two reactions in a single solution, and we can identify four sets of conjugate acid-base pairs as follows. So this one is the base 2, base 1, then the acid 1, and the acid 2. Okay. pH as a measure of acidity. In actuality, the concentration of hydrogen positive is very small. The pH scale was developed to provide an easier way to determine whether a solution is acidic, basic, or neutral. It is a logarithmic scale, base 10, where pH is equal to negative log H positive. Consider the concentration of H positive in equation 9. If we calculate for its pH, pH is equivalent to negative 7 is equivalent to 7. So this one, negative times negative will be the positive. So, because pH is calculated as a log base 10. For every power of 10, the pH changes by 1. It is also important to remember that as the hydrogen positive increases, the pH decreases. So how we identify whether a solution is acidic or basic using the pH scale. Number 1, the solution is neutral. If hydrogen is equivalent to 1 times 10 to the negative 7 power, pH is equivalent to negative log over 1.0 times 10 to the negative 7 power is equivalent to 7. So meaning to say, if our solution is neutral, the product would be 7. So if it is acidic, it should be greater than, no, less than by 7. If it's basic, this is less than by 7. Right? So these are the example solution at this pH. So pH 0, so very acidic. So this is the battery acid, the strong hydrochloric acid. So we can determine the pH level of each example. Tomato juice, acid rain, they have pH 4. The seawater, we have pH 8. Pure water, it's pH 7. Ammonia solution, we have pH 11. Okay. Strength of acids and bases. Strong acids are acids that completely dissociate or ionize in water. This is the example of strong acids are the inorganic types, including hydrochloric acid. Strong bases in similar contexts are bases completely ionized in water. Weak acids are acids that ionize limited extent and at equilibrium. The resulting solution will be a mixture of the ionized and unionized form of the citric acid and ascorbic acid. So weak bases have similar properties to weak acid. Example is the ammonia or ammonia hydroxide and methylamine. Diprotic and polyprotic acid. All the examples of chemical equations are ionization of monoprotic acid. This acid can donate a single proton, hence mono. So meaning is single or one. However, there are acids that has more than one proton to donate. This is what you call diprotic, 2 protons. And polyprotic, it is the more than 2 protons. While the calculation involved with these acids are similar to monoprotic acid, it is not as straightforward because diprotic and monoprotic acid, it is not acid lose 1 proton at a time. This means a diprotic acid will have 2 ionization reactions, while a polyprotic acid can have as many as its proton available for donation. Titration of acid and bases. There are 4 types of acid-base titration, and we will briefly discuss each. The first titration is between a strong acid and a strong base. This reaction is a neutralization reaction as shown in the sample chemical equation using hydrochloride and Na0H as example. So as we have learned before, sodium and chloride do not affect the acid-base reactions. Hence, considering only the species involved in acid-base reactions we have. So let's take a look at pH profile or titration curve determined from titration of a strong acid with a strong base. So as you can see, this is the equivalence point. This is the 7. So andito yung acid, this is the base. This is the sample titration curve. A strong base run into a strong acid. Strong acid, then going to the base. The second titration is a strong acid against a weak base. At the beginning of the adding a strong acid to a weak base, the pH changes is more obvious compared to a strong acid, strong base system. However, it will reach a point where the change in pH is lower, meaning the plot is less steep. At this point, in addition to the weak base and strong acid, the conjugate acid of the weak base is now part of the solution. A mixture of a weak base and its conjugate, as we have learned previously, is a buffer. So this is the rapid fall of pH to start, but the rate of fall slows down. So hindi siya ganun kabilis. So pabagal-bagal hanggang sa maging acidic. So this is the third titration setup between strong base and a weak acid. Okay. Next is the fourth titration system, is the reaction between a weak acid and a weak base. So this titration produces both the conjugates for the weak acid and base, and that means the final solution has a tendency to act as a buffer. That is why in weak acid, weak base titration, you cannot find the steep point when equivalent point is almost reached. Okay. Solubility equilibria. Solubility is a physical property referring the amount of solute dissolved in water to achieve a saturated solution. It can be expressed in several terms such as solubility gram per liter or molar solubility M. Like the ionization reaction, the solubility equilibrium depends on the constant. The solubility product constant, or K, is calculated as follows. So Ksp is equivalent to product over the reactants. Solubility equilibrium is reached when there is no change in the concentration of the product and the reactants. Solubility equation for salt is similar to the ionization of weak acids and bases. Not complete dissociation, the solubility equilibrium is also affected by several factors. But for this module, we will look at how the common ion and pH affects solubility. Thank you very much.